In today's video, we're going to talk about hybrid orbital theory. Now, VSEPR theory tells us about the shape of a molecule, but those shapes do not correspond to the shapes of the orbitals that come from quantum mechanics. So that was a problem, and the way we overcame that problem was through hybrid orbital theory. Now, this was proposed by Linus Pauling, and this idea of the orbitals within a molecule are no longer atomic orbitals like in quantum mechanics, but they're part of the molecule. They're hybridized. And that actually, the concept of hybridization actually leads to where the VSEPR shapes are. So, what are the basics of hybrid orbital theory? First, we need to mix at least two non-equivalent atomic orbitals. So, for example, an S and a P, or an S, a P, and a D, or S and two Ps. So these different shaped orbitals. And the hybrids are going to have a very different shape from the original atomic orbitals. Also, orbitals are conserved. That means that the number of hybrid orbitals is equal to the number of atomic orbitals used in the hybridization. So, for example, if I use one S and one P, I'm going to make two hybrids. If I were to use an S and two Ps, I would make three hybrids. So once you've made your hybrid orbitals on your central atom, then you can form a covalent bond through the overlap of the hybrid orbitals with atomic orbitals of the incoming atom, the surrounding atoms, or with other hybrid orbitals of another atom. So it's this orbital-to-orbital overlap that constitutes the covalent bond. Alright, so let's talk about the combination of an sp hybrid. Now, this is something like for beryllium chloride. This hybridization occurs on the beryllium. So we take an s orbital in the beryllium and the empty p orbital. They're going to mix together to form two brand new sp hybridized orbitals. You can sort of think of this in terms of the electron configuration for beryllium. Beryllium having its 1s shell filled, so the 1s. It's got the 2s, and that's got two electrons in it. And it also has the 2p, but they're not filled. Now what if we take one of these s electrons and we were to promote it to a p? And then those two orbitals were to mix together. That is really what we have with the sp hybrids. This can happen because, remember, the s orbitals and the p orbitals are fairly close in energy. And this combination of making a hybrid orbital actually lowers the energy of the molecule so that it can form this sp hybridized orbital and then form bonds. Also, remember that we took two orbitals and we formed two orbitals. Orbitals are conserved. Two orbitals starting with, two orbitals that we end with. The formation of an sp2 hybrid comes when we take an s orbital and two p orbitals. So this would be something like boron trifluoride, BF3. Remember, in boron, we've got, I'm going to just do the valence shell, we've got the 2s orbital, and we've got the 2p orbitals. So the 2p orbital, it's got one electron and the 2s is filled. If we promote one electron there and mix this p, and this s, so the s, the p, and the p, the hybridization yields three new sp2 hybrids. It's an sp2 because we use two of the p orbitals. Now look at the shape of these things. The directionality that this hybridization gives us is 120 degrees apart from each other. Which we know that boron trifluoride is a trigonal planar molecule. So this hybridization corresponds with the shape from the VSEPR theory. Formation of the sp3 hybrids requires one s and each of the three p's. When you hybridize these orbitals, they point to the corners of a tetrahedron. So this gives us a tetrahedral geometry. So something like methane, CH4, that carbon would have sp3 hybrids. So let's take a look at how we form the bonds of something like these sp3 hybrids in the methane. So the carbon has 4 sp3 hybrid orbitals, each pointing to the corner of your tetrahedron. And then the hydrogen atoms with their 1s atomic orbital come and overlap their atomic orbital with the hybrid orbital on an end-to-end basis and form the bond. So the portions that I've colored in are what corresponds to the formation of a covalent bond. Now let's look at an sp3 hybrid in ammonia. So how does the sp3 hybrid work in ammonia? Well, let's take a look at nitrogen's electron configuration. And I'm only going to do the valency. We've got our 2s, and we've got each of our 2p's. And remember, we have a full, half-full 2p subshell. So how are we going to mix this? Well, if the orbitals just all go ahead and mix, notice I'm still left with a pair. But that lone pair will occupy one of the sp3 hybridized orbitals. And then that still gives me these 3 available orbitals for bonding. And when we do this, we see that we still have the tetrahedral electron domain geometry, right? Well, we can also predict the correct bond angle because we know the size of the lone pair is going to be large. So we knew that this bond angle here, the hydrogen to nitrogen hydrogen bond angle, must be less than 109.5. Similarly, you would see that for water, again, the oxygen would be an sp3 hybrid as well, but this time you'd end up with 2 lone pairs. So in water, it would look very similar to this picture for nitrogen, except instead of 1 lone pair, you'd have 2 lone pairs. So predicting the hybridization of the central atom is actually fairly easy. It requires you to be able to draw the Lewis structure. Everything in this chapter so far has required you to be able to draw the correct Lewis structure for the molecule. Then you're going to determine the electron domain geometry, the number of lone pairs and the number of atoms. Okay, so it's lone pairs and atoms, so the electron domain geometry. So if your electron domain geometry, you have 2 total regions of electron density around the central atom. We said that was the linear electron domain geometry. The hybridization will always be an sp. So anytime you have a linear molecule and there's only 2 bonded atoms and no lone pairs, you're going to have an sp hybrid. If you've got 3 atoms and or lone pairs, your hybridization will be sp2. 4 total groups, sp3. 5 total groups, sp3d. And 6 total groups, you're going to have sp3d2. Now, you'll notice that this is dealing with the electron domain geometry. So, linear, trig planar, tetrahedral, trigonal bipyramidal, so trigonal bipyramid, and octahedral. So not all linear molecules are going to be sp hybrids. For example, in trigonal bipyramidal, if you had 2 atoms and 3 lone pairs, that was also a linear molecule. In that case, the hybridization of the central atom would be sp3d. So you have to be able to get your electron domain geometry. That is absolutely key. From your EDG, you'll be able to tell the hybridization. So this table just summarizes all of the things that we've seen. When you have an sp hybrid, you have a linear molecule. sp2, trigonal planar. sp3, tetrahedral. sp3d is your trig bipyramidal. And sp3d2 is your octahedral. So you know your electron domain geometry, you'll know your hybridization. Now we're going to use hybrid orbital theory to explain some different bonding motifs, especially in carbon. So let's take a look at the sp2 hybridization of carbon. In the ground state, you've got the 2 s electrons and 2 2p electrons. If we promote one of the s electrons into a p orbital, and then hybridize the s and only 2 of the p's, we're left with a lone electron in the 2p orbital. Now that lone electron is kind of special. So the sp hybrids are given here in green. They are pointing to the shape of a triangle, the trigonal planar portion. sp2, trigonal planar hybridization. That leaves that free electron in the gray space, which is perpendicular to the plane of the hybrid orbitals. Now, this is where it becomes kind of fun. If we take a look at ethylene, C2H4, the carbons are sp2 hybrids. They are trigonal planar. Let's take a look at the Lewis structure real quick. There we go. There's our Lewis structure. These guys are trigonal planar. Now, the overlap here, this end-to-end overlap of the sp2 hybrid orbitals, gives us the bond between the 2 carbons. But that's only a single bond. The double bond comes from the side-to-side overlap of those unhybridized 2p orbitals. So what you get is you get an area of electron density above and below the bond axis, as well as through the bond axis. The area of above and below the bond axis is known as a pi bond. Okay? Pi bond. This is the second bond in a double bond. The first bond is always a sigma bond. This is the end-to-end overlap that occurs between the 2 atoms. So this is within the plane for the sigma bond. The pi bond is above and below the plane. All first bonds are sigma bonds. So here we can see the pi bonding interaction within ethylene, and then here we have our molecular model with our isoelectric map. And you notice that we've got these 2 areas of high electron density. We know because they're red. Those 2 areas of high electron density are that double bond. So if we count the types of bonds that we have available, if we have a single bond, it must be a sigma bond. Must be a sigma bond. A double bond consists of 1 sigma and 1 pi. And a triple bond is 1 sigma and 2 pi. Now if we take a look at the sp hybridization of carbon, if we promote our 2s electron to the 2p, but we only hybridize 2, that leaves us with 2 open unhybridized p orbitals. Those 2 open unhybridized p orbitals are going to be available for bonding. So for acetylene, C2H2. There's our Lewis structure, C2H2. We made an sp hybrid. The sp hybrid orbitals on the carbons are shown here in red. These are linear. Sp hybrids are linear. That leaves two p's to be above and below the bond axis, and then also two p orbitals to be to the side of the bond axis. So what you get is this pi bond overlap both above and below and to the sides. So here you have the purple is the sigma interaction, and then you have 1, 2, 3, 4 areas of pi interaction. Remember, these 4 areas of pi interaction are only 2 bonds. So here we have a triple bond. If you were to cut a cross section out of this, what you'd see is sigma bond. Okay, that's the area of sigma bond electron density. And then you'd have pi bond density all around. And if we take a look at the electrostatic map of acetylene, you can see that you have a high electron density all the way around the center of the molecule. That corresponds to the above and the below pi bond and the side-to-side pi bond. So in review, hybrid orbital theory takes two or more non-equivalent orbitals and combines them to make two or more hybrids. These hybrids exist on the central atom. Orbitals are conserved. If you use two atomic orbitals, you make two hybrids. If you use three atomic orbitals, you make three hybrid orbitals, and so forth. In order to determine the hybridization of the central atom, you need to know your electron domain geometry. The electron domain geometry tells you the hybridization. If you have an electron domain geometry with 2, you have an sp situation. 3, sp2, 4, sp3, 5, sp3d, and 6, sp3d2. Now, through hybridization, you can have all sorts of different interactions. You can have sigma interactions. This is the end-to-end overlap of orbitals. Or you can have pi interactions. This is the side-to-side overlap of atomic orbitals, such as we saw in ethylene and acetylene.